Harnessing chemical energy. We know that when a chemical reaction occurs, energy is exchanged due to the fact that the chemical bonds are formed or broken during the process. So if we have a compound, we could break it into two elements, or you could just add two elements together and make a compound. But when this thing happens, then either they will produce the energy, or it means they release the energy, or they consume the energy in order for that process to happen. During the chemical reaction, energy can either be absorbed or liberated. Energy in a reaction. A reaction in which energy is given off is called exothermic. And the example is hydrogen burning, that whenever you are adding hydrogen to oxygen, it gives off water as well as it gives out huge amount of energy too. A reaction in which energy is absorbed is called endothermic reaction. The example is nitric oxide. So formation of nitric oxide consumes the energy, and formation of water releases energy. So the one which releases energy is called exothermic. The one which consumes the energy is called endothermic reaction. Exothermic chemical reaction, energy is released in the form of heat. An example, the chemical combination of gas, oil and oxygen in your wheat eater. So that gives off heat. Metabolizing sugar in the human body. So whenever there is any food we consume, so whenever the food is added to the body, that releases energy. That is, digestion process releases energy that is needed for the whole body to act or function. Endothermic chemical reaction. It requires external source of energy to occur. Endothermic reactions result in electrons with increased amount of energy. The chemical change that occurs when you fry an egg is an example of endothermic reaction. So whenever we want to fry an egg, we have to heat it up, and when we heat it up, so it just consumes energy and it just turns into the way we want it. The reactants have more energy than the products. The dissociation is an endothermic process. So if you have a compound and if you want to break it into two pieces, which is two materials, then it is called the dissociation process. For example, if you have water and if you are trying to break that water into hydrogen and oxygen, then this is called a dissociation process. And this requires energy. And energy must be released as the product form. So whenever the products are whenever the products are formed, the energy will be released. The container in which exothermic reaction is taking place will feel hot. So the container in which the exothermic reaction is taking place will feel hot, is a hot place. The reaction where it takes place, it gives a hot environment. The reactants have more energy than the products. So you can see that if you want to break hydrogen, you give energy and it breaks into hydrogen and oxygen, and in this case the energy used is 13.6 kilojoules of energy. The products that have more energy than the reactants, the energy must be absorbed as the products form. So whenever products are formed, the energy must be absorbed. And the container in which the endothermic reactions taking place will feel cold. Okay, so because the energy is absorbed, so the container will be cold. By conservation of energy, the reverse of an exothermic reaction must be an endothermic reaction. So it means if you are making hydrogen and oxygen combine together to make water, and the water breaks into two, which is hydrogen and oxygen. So these two are, one of them is endothermic and the other one is exothermic, and these two are opposite of each other, and the amount which is released in forming of water is exactly same amount needed for the water to break down into hydrogen and oxygen. The energy given off in the former must be equivalent to the energy absorbed in the later. Endothermic example, dissociation of salts. When potassium nitrate is dissolved in water, the container will become cold. So the application is cold packs. Exothermic reaction, the example is neutralization. When any acid is carefully mixed with the base, the mixture will become hot as the water is generated. So whenever the exothermic is giving the heat off, so whenever the reaction is done, the reaction results in a hot environment. And endothermic, which consumes energy, so because it consumes energy, the output, whenever the reaction happens, the whole environment becomes cold. Solubility of chemical compounds. A chemical compound is called stable if a large amount of energy is required to cause a chemical change. So if it is hard for us to break the compound, it means it's a very stable compound. A compound, whose decomposition is strongly endothermic, is stable. So if at all we are trying to make the if you are trying to decompose, then if you need to give more and more energy or a high amount of energy, then it is a stable compound. If the decomposition is either weakly endothermic or exothermic, the compound is unstable. So either when you want to break a compound, if it is easily breakable, then it is an unstable compound. If the formation of a compound is strongly exothermic, then the compound is stable. Okay, so whenever you are trying to add two materials together, and if it gives a huge amount of energy, then it's a very stable compound. If the formation results in a weakly exothermic or endothermic, that results in a unstable. So if it gives off huge amount of energy when they are mixed together, it means it's a very strong or stable compound. It gives little amount of energy, then it's a weak or unstable compound. Since the chemical reactions involve the rearrangement and exchange of electrons between constituents, we can conclude that chemical energy is electron potential energy. So the energy can be transferred from one to other, but it cannot be created or destroyed. So whatever the chemical energy is, that is the potential energy of the electron. And is an endothermic reaction, the electrons in endothermic reaction, the electrons in the products have higher potential energies than before the reaction. In an exothermic reaction, the electrons in the products have lower potential energies than the before reaction. We have thus so far discussed the details of the reactions. Now we turn the question of how the reaction begins. We have seen that some reactions require energy to start. For example, the hydrogen burning. While hydrogen is highly volatile, the explosion will only begin if set off by some source of spark. So we have seen that, when you're mixing together, you get the energy out. When you're breaking something, then you need the energy. But some reactions, what they do is they need a little bit of push for the reaction to start. But once the reaction starts, when the compound is formed, it gives huge amount of energy. So example is hydrogen burning. Even though hydrogen and oxygen reaction gives the huge amount of energy, initially we need to supply some amount of energy in order for the reaction to start. So this amount of energy we give is called the activation energy, the energy needed to start a chemical reaction. It is very low for some reactions and it is very high for some others. Not all chemical reactions require activation energy. The reason behind the activation energy requirement is in the electron potential energy of the constituent material. So some reactions require some little bit of energy supply before it takes place. Some of them, they readily react and give out the energy, or they readily react and consume the huge amount of energy. If something needs a tiny bit of amount of energy to react, but it gives out the huge amount of energy as an output, then we call that tiny amount which is supplied in the initial stages, that is called the activation energy. When two atoms combine, bonds must be formed. Bond formation is an energy releasing process. Whenever there are any bonds formed, then they release energy. In order for the chemical reaction bonding to occur, other bonds may need to be broken, which requires additional energy to the atom or the molecule. Much of the modern life is centered around the chemical reaction combustion. The energy is released during this common exothermic reaction that is used to produce mechanical and electrical energy that powers the modern life. Materials used for these combustion reactions are actively known as fuels. Fuel should be inexpensive and widely available. Fuel should be easily obtainable and storable. So these are the desired properties of fuels. It should be cheap, should be abundant, and it should be easy to store and easy to access. Ideally, the end products of the combustion of the fuel should not be harmful to living organisms. Something like we use the petrol and we use all these gases and they leave out carbon dioxide. So that is not really good. So we should have a fuel. It should last forever, it should be cheap, and it should be easily storable, and it should not hurt the environment. This requirement is met by only few fuel sources. The typical fuel sources are carbon-based compound, which are also known as fossil fuels, which has a major impact on the environment because most of them are coal-based or carbon-based. So they give out carbon dioxide as the byproduct. So that is not good for the environment. Common examples of the liquid fuels are gasoline, kerosene, diesel, heating oil, and these are all hydrocarbons. The benefits of these liquid fuels are they are strongly exothermic. Large energy is released when it is combusted. So the problem with it is it releases either carbon dioxide or carbon monoxide, which is a very toxic gas for the living organisms. Partial solution, catalytic converter. So catalytic converter is something called, it will make the combustion process occur 100% at the same time faster. The common examples of gas fuels are natural gas, which is methane, butane. The benefits, these are a little bit better or cleaner, I should say. Benefits, much less pollutant production than the liquid hydrocarbon fuels. The problem is not quite as efficient in energy production as the liquid hydrocarbons. Even though they are a little cleaner energy sources, but still they are not as efficient as the other fossil fuels. So these are not quite commonly used as the others. Solid fuels. Common example is coal. Coal use has decreased as the use of petroleum products has increased. Benefits, it's widely available, fairly abundant. The problems with it is the most coal is not pure. It contains varying amounts of sulfur. When it is burned, the sulfur is released. When the sulfur combines with rain, the oxides and sulfur goes into the solution, forming sulfuric acid. This is called acid rain. And acid rains are not at all good. This is a very environmental unfriendly use of coal or the fuels.